Now, gravitational potential energy is not the only type of potential energy. We can actually also store potential energy in a spring. So let's consider what happens when we first of all put a mass onto the spring, and then when we extend the spring further. We'll look at how much work we have to do in order to do this. Okay, so when I place my mass on my spring extends and I have a new equilibrium position right here, and at this equilibrium position the spring force, which is pulling the spring back up to its old equilibrium position when it didn't have the mass on it, is equal to the weight force of the mass which is pulling it downwards. So I've got a weight force downwards mg and a spring force which ends up being upwards, and it's described by Hooke's law. F is equal to minus kx. The minus here is because it's a restoring force. It acts back towards the equilibrium position. Now let's consider what would happen if I want to extend the spring away from this equilibrium position. I need to do work in this case to move the mass from some initial position, let's call it x subscript I for x initial, to some final position, let's call it x subscript f. Now, in order to calculate the work, I'm going to need to use my equation that the work done is equal to F dot S, where S is the change in displacement. Now, what's difficult about applying this equation in this case as opposed to the gravitational case is that my force actually depends on my displacement. The force is given by minus kx instead of just being a constant and independent of where I'm actually considering it. So because of this, what I need to do is break my extension up into lots of little components, and over each of those little components the mass moves a very small distance, let's call it dx. So say this is position x, then a little bit further down is a position x plus dx, and between x and dx I can assume that my force is constant. If that's not true, then choose a smaller dx to make it true. Okay, so let's calculate how much work I have to do on my spring to move the mass from the location x to the final location x plus dx. So in this case, the work is equal to F dot S, which is equal to minus kx times, now it'll be my final position minus my initial position, so it'll be x plus dx minus x. So this will be minus kx dx. So now I know how much work I need to do on the mass to move it through a little increment. So what I'm going to do is split my extension from some initial location, x initial, to some final location, x final, up into lots of little increments, and each of those little increments has a length, an extension, dx. And to calculate the total work, I just need to sum the work done to move it through each of those little increments individually. Now, if I'm going to sum, that's actually just integrating it. Integrating it is literally doing doing a sum over very small increments. So my sum over increments dx from x initial to x final, I can write as the work is equal to the integral from x initial to x final of what we just calculated, minus kx dx. So I'm now just doing a simple integral. So when I do this integral, I end up with minus kx squared on 2, and I need to evaluate that at x final and x initial. So this is equal to minus kx final squared on 2 plus kx initial squared on 2. So that tells me about the amount of work that I have to do to extend this spring. So just to recap, as this is the first time you've seen an integration set up in this way, and it's a very important technique, we're going to have a look at this in a few different representations. So what we're trying to do is to calculate the work done by the spring force, F is equal to minus kx, as the spring moves from some initial position here to some final position here. And the difficulty here is that the force is different at different places. So at x initial, we've got an upwards force like that, and then at x final, we've got a larger upwards force as xf is greater than x initial. And these forces are upwards as the spring is moved away, downwards, away from its equilibrium position, and so this is a restoring force. Okay, so what we're going to need to do is break this movement from x initial to x final into a whole lot of little segments. So here's our mass at x initial, here it is at x final, and we consider just one place here, x, and then we can consider another place nearby, x plus dx. So this change in height between these two here is dx, and we choose dx small so that f equals minus kx is constant over dx. And we can always do that. If it's not true, then we choose a slightly smaller dx. So then what we can do is calculate the work done from x to dx, and when we do that, the work done is equal to F dot S, and the force we've said is constant, it's minus kx, and the change in the displacement, the distance it moves through, is dx. So this is the work done to move at this very little increment dx. Now the total work is the sum of the work done to move through each increment from x initial to x final. So what we want to do is the sum of the minus kx dx, and this is from x is equal to x initial to x is equal to x final. But because dx is a very small increment, this is a sum with lots of little parts, so this is literally just what integration is. So this is the integral of minus kx dx from x initial to x final. So that's why this integral sign looks a bit like an S, because it is literally a sum over small increments. Okay, so now we can solve this integral, and this will be equal to minus kx squared on 2, because we're just integrating something which is x, and then we've still got k, which is a constant, from x initial to x final. So this is equal to minus kx final squared on 2 plus kx initial squared on 2. Now the other way we can think about this is to think about drawing a little graph of it. If we were to plot a graph with force here and displacement here, we want to do this where the displacements go from x initial up to x final. Okay, so let's start by considering the force here is given by minus kx initial. So let's draw the magnitude of the force, and here we've got the height is given by kx initial, and then this width is dx, and then we can consider the next increment, which is xi plus dx, and there we'll have a just slightly higher force, and so on. We consider each increment, and we'll end up with something like this, and then the work done is equal to the area under F versus S graph. So we'll end up with a straight line going up like this, and to find the area under a graph, we can just integrate it. So we'd end up with the same integral if we considered it graphically like this as well. Now, often we'll be considering the case where we start from equilibrium, so where
x initial is equal to 0, and we'll say x final is equal to x. So this is just considering the work that we need to move a mass from any point 0 on the spring down to any final point x. So in this case, we've got that the work done, which we've calculated over here, so the work done is equal to minus kx final squared, so that's x squared on 2, plus kx initial squared, which is 0 squared on 2, so that's equal to minus kx squared on 2. So that's the work done by the spring force, so the change in potential energy, which is equal to the negative of the work done, is equal to kx squared on 2. So that's the amount of potential energy that you store in a spring as you move it from its equilibrium point to a position x away from the equilibrium point.
Now we can actually calculate the speed with which the mass on the spring will move by considering energy. So at this point where it's stationary, it's in equilibrium. If I extend it down to some amplitude a, so it's moved through distance a now, then it's got potential energy stored in the spring. When I release it, this energy converts between potential energy at the two extremes and purely kinetic energy right in the middle. So we can calculate the potential energy stored in the spring when I displace it, because we've said that the change in the potential energy is equal to a half kx final squared, which is a half ka squared in this case, minus a half kx initial squared, and in this case x initial was 0, it was at its equilibrium position, so the displacement from equilibrium is 0. So the change in potential energy is given by a half ka squared. And so that energy, the half ka squared, is conserved, is just converted between different forms as the mass moves. So we can have a look at this on tracker. You'll be able to see that the speed with which the spring is moving oscillates like this, and the maximum speed is right in the middle of the motion when the mass is at its equilibrium point. Now we can use this energy conservation to calculate the speed of our mass. So the total energy within the system is given by the change in the potential energy, the work done as we extend the spring, which is a half ka squared, and this is then in the form of potential U plus kinetic k. The potential is given by a half kx squared, where x is the displacement from equilibrium, and the kinetic energy is given by a half mv squared. So we've now got a half ka squared is equal to a half kx squared plus a half mv squared. So we can rearrange this. We want to put v on one side, so we've got mv squared is equal to ka squared minus kx squared. We've cancelled off all the common factors of a half there. And so you can see that the speed is going to be equal to the square root of k on m times a squared minus x squared. So we've now used energy to come up with an expression for the speed of the spring. So we can actually come up with this expression another way using the equations that we gave for a body undergoing simple harmonic motion when we were looking at simple harmonic motion. So let's have a go at that now.
Okay, so when we did consider simple harmonic motion, we said that the displacement was equal to a cos omega t plus phi, and we showed that for a mass on the spring, omega was equal to the square root of k on m. Now, what we've just shown is that v is equal to the square root of k on m times a squared minus x squared, and we showed this with energy considerations. But because it's fun and it gives us a bit of practice using calculus, we can also derive this another way, as we know that v is equal to dx dt. And so we just need to take the derivative of our equation up here with respect to time. So when we do that, we end up with minus a omega sine omega t plus phi. So in this case, the negative came about because when we differentiate a cos, we get a negative sign, and then the omega out the front comes from this term in here. When we differentiate the term underlined in purple with respect to time, we end up with omega. So that's where that omega came from, and then it's times sine omega t plus phi. Okay, so now what we can do is we can use the fun trigonometric rule that sine squared theta plus cos squared theta is equal to 1. So we can write, well, x squared is equal to a squared cos squared omega t plus phi. And we can also square an expression for velocity. So we have v squared is equal to a squared omega squared sine squared omega t plus phi. And then substituting our expression for omega from up here, we have this is equal to a squared k on m times sine squared omega t plus phi. And then we can write this as a squared times k on m. Now, sine squared omega t plus phi, we can rearrange using this. We've got sine squared theta is equal to 1 minus cos squared theta. So this tells us that sine squared omega t plus phi is equal to 1 minus cos squared omega t plus phi, just letting theta equal omega t plus phi. So I'm going to write this in here. I'll have 1 minus cos squared omega t plus phi. And we can then put the a squared inside the bracket. So we've got k on m times a squared minus a squared cos squared omega t plus phi. But a squared cos squared omega t plus phi from up here is equal to x squared. So now we can substitute that in. We've got k on m times a squared minus x squared, which is really cool because now we have shown this expression up here. If we take the square root, we've got v is equal to the square root of this thing, which is k on m a squared minus x squared. So we have now shown our equation for the velocity using the equations for the displacement and also using the energy considerations.